Hi, my name is Erin Roy and I'm a senior psychology major at UNC. A fun fact about me is that I enjoy baking in my free time. I've mentored for CHEM 101 3 times before and I'd like to mentor for CHEM 101 again this semester. The problem that we're going to do today is this: whether nitrate is polar or nonpolar. I like this problem because it combines a lot of different concepts. So first, what I would tell students is to make a tally of their valence electrons so we can draw the Lewis structure of nitrate. So we know that nitrogen has 5 and oxygen has 6, but there's 3 oxygens. And this minus charge up here we're going to count as 1. So that adds up to 24 valence electrons. I would start with nitrogen in the middle and then make bonds to all the oxygens. So we used up 6 electrons and we're left with 18. Now I'm going to fill in the electrons on all the oxygens and see what we're left with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we used up all of our valence electrons. Now we're left with negative formal charges on all of the oxygens and a +2 formal charge on the nitrogen. The nitrogen also has an unfilled octet, which we know is not good. So this is definitely not the best resonance structure that we can draw for this molecule. Now, why don't we move down one of the lone pairs on one of the oxygens to make a double bond to nitrogen and see what that leaves us with. So we know we have negative formal charges on these 2 oxygens. Now we have no formal charge on this top oxygen, and we have a +1 formal charge on this nitrogen. Now, I know it might be tempting to move this lone pair here to make a double bond to the nitrogen, because that would get rid of this formal charge and this formal charge, but then that would leave us with an expanded octet on the nitrogen, and because nitrogen is in period 2, it can't have an expanded octet. So this seems like the best structure that we're going to get. And because of the symmetry of this molecule, we can get different resonance structures that are just as good as this structure. So we can move the electrons and make the double bond here. And we can do the same thing for this oxygen. Oh, whoops, I do the same one over again. Okay, so now we're left with 3 resonance structures, but this still isn't enough to answer the question. So although these resonance structures are each a good way of representing the molecule, they're not the best way. In actuality, none of these resonance structures actually exist. These are just different representations of the one molecule, and we can combine all 3 of these in a resonance hybrid to show what the molecule actually looks like. So if we put all 3 of these together, we're left with partial double bonds to the nitrogen, partial negative formal charges, and nitrogen always has that +1. Because of the symmetry of this molecule, we can say that it's nonpolar. If we draw bond dipoles going this way, and then we draw 2 going this way, break it up into the vectors, we can see that these 2 vectors add up to the magnitude of this one and cancel each other out, and these 2 are the same magnitude and they're going in opposite directions, so they cancel each other out as well. showing that this molecule is in fact nonpolar because the dipole is canceled and it has no net dipole.